Hello everyone. In this video I'll be talking with you about Thevenin equivalence. And so this is just an introduction to the theorem itself. So I'll be using a very basic circuit structure here in order to do that. So what is a Thevenin equivalent? Well, a Thevenin equivalent is basically summarizing any complex network of circuitry to consist of only a Thevenin equivalent voltage in series with a Thevenin equivalent resistance. So it's the net voltage in series with the net resistance of the entire network at these two terminal points of the circuit itself. So there's two methods to go about in determining that, and I'll be going over both of those methods. Method one is simply to have the open circuit voltage be VTH. And in this very simple case that we have here, we can see that the open circuit voltage, which is the voltage of the circuit with no load connected, okay? So you're not going to have any loads connected, and you're going to say, what is the measurement of that open circuit voltage? Well, this is just very simple in our case here. That's a voltage divider network. Okay, and that amounts to, this is R2, R1, VDC, then it is VDC times R2 over R1 plus R2 is going to give us V open circuit, which is equivalent to VTH. Okay, so next we're going to take that open circuit voltage and we're going to divide it by a short circuit current. So what does that mean? Well, we'll have the very same circuit and we are going to short that circuit where you would normally have your VOC. Okay, it's at that same location. We're going to short that circuit, and what we want to find out is, what is it? Well, if we short that circuit, then R2 comes out because all of the current gets diverted around R2 because it's being seen as a very large resistance now. And with that being the case, it's not there, and so you don't have any voltage drop across a wire that has no resistance. So therefore, all we have left into our circuit is VDC and R1 in series with each other, going like this, where you only have ISC. Okay, so then it becomes VDC over R1 equals ISC. Now, again, our VOC was equal to VDC R2 over R1 plus R2. Now, with that being the case, what we can do now is go ahead and calculate. So VOC over ISC equals VDC R2 over R1 plus R2 divided by VDC over R1. Now, as you can see, VDC cancels and you have R1 on the top, and so VOC over ISC equals R1 R2 over R1 plus R2. Okay, that would be RTH. So that is it. That is all we need to do in order to use method one. Now on to method two. Method 2 for VOC is still the same as method 1. So again, restated, VOC equals VDC R2 over R1 plus R2. Okay, and so then next we're going to have VT. Well, what is VT? VT is a test voltage. In order to apply that test voltage, there's one thing that we have to do first. What we have to do is we have to suppress all of our independent power sources. In this case, for us, it means that direct current voltage source. So VDC, we need to suppress that. And when we do suppress it, because the resistance for a ideal voltage source is 0, we're going to replace it with a wire. If it had been a current source, we would replace that with a open, because the internal resistance for a current source, ideal current source, would be infinity. But in our case, we have a ideal voltage source, so we are going to replace that with a wire or with a short circuit. Okay, and so we have this case, and we still have our circuit here, and that will be VT, will be at those 2 points. And so we are going to use VT in order to figure out what is ISC. ISC, or it's not ISC, it's IT. What is IT? IT is going to be corresponding to VT, which is the same thing. It's the current that's coming from VT. So it's going to be your test current. And you're going to take that test current and you're going to put VT on top of that. And so you're going to have VT divided by your test current, and then that's going to give you RTH. Okay, so VT is pretty straightforward. Usually what you do for it is you use a convenient value like 1 volt when you actually have numbers to work with here. But VT in our case is just going to be kept as a reference designator itself. And so VT is just plain old VT. And all we need to really figure out is, well, what is IT? Well, VT, okay, divided by our net equivalent resistance of all of this over here is going to give us IT. Now, with that being the case, what is our net equivalent resistance? Well, as you can see, R1 is in parallel with R2 from the point of what VT sees effectively. We can just draw that to make it look, make it more familiar looking by sliding it over there, and we can see R1 is in parallel with R2. So our equivalent, okay, is going to be R1 parallel to R2 equals R equivalent. And so that will give us IT. Now, next step is, now that we have IT, we're going to take VT, put it over IT, and that is going to give us RTH. So VT over IT, and what is IT? IT is VT over R equivalent. So VT over R equivalent, that's going to give us RTH. And so we can see that we have our VTs cancel, and R equivalent comes up to the top. And what is R equivalent? R1 parallel to R2, which is R2, R1 over R1 plus R2. That's RTH. So we can see in both of these cases, okay, both of these cases, we end up with RTH equals R2, R1 over R1 plus R2, and VTH equals VDC times R2 over R1 plus R2. In both cases, no matter what method we use. Okay, and so it's up to you with which method you prefer to use. What do you want to, which one is easier for you, whatever is most convenient. It's totally up to you to determine which one, but that is basically the Thevenin equivalent, the basic ins and outs of the theorem itself. So hopefully this video was helpful for you. Thank you for watching and have a nice day.